Slide 1. Cover, QA&TEST Embedded 2025, the 24th International Conference on Embedded Software Testing, 22 to October 24, 2025, Euskalduna Palace, Bilbao. Slide 2. Greetings, welcome everyone. Today, we're going to delve into the critical and rapidly evolving field of testing AI-based software systems. We will bridge the gap between the theoretical foundations and the practical applications of quality assurance for these intelligent systems. My name is Shay Ginsbourg and I am excited to share my insights with you. Artificial intelligence is increasingly integrated into critical software systems, transforming industries and daily life. However, the unique characteristics of AI, such as learning capabilities, data dependency, and opaque decision-making pose challenges for traditional software testing. This paper provides a comprehensive guide to testing AI-based software systems, bridging theory and practice. It explores foundational differences from conventional testing, outlines key challenges, presents practical methodologies, and highlights best practices and future trends. Slide 3, about the speaker. Before we dive in, a little about me. I am experienced in AI-powered software testing, performance, and load testing, and I also work as a freelance biomed regulatory affairs consultant. I am a lecturer at Sami Shimon Academic College and the founder of Ginsbourg.co.il. My experience in these diverse areas has given me a unique perspective on the challenges and opportunities in testing AI systems, which I am eager to share with you today. Slide 4, Introduction. AI Springtime. AI is here to stay. To understand where we are, it is important to look at how we got here. This timeline shows the journey of AI, from its early concepts to the AI spring we are experiencing now. The AI winters were periods of reduced funding and interest, largely because the hardware and algorithms of the time could not keep up with the ambitious ideas. But with the rise of GPUs and massive datasets, we have overcome many of those limitations. Alan Turing's foundational work on computability and the Turing test laid the theoretical and philosophical groundwork for modern artificial intelligence, establishing him as the field's tragic hero and primary visionary. We have seen incredible breakthroughs, from Deep Blue defeating a world chess champion to the generative AI like ChatGPT that is transforming how we interact with technology. This is not just a passing trend, AI is fundamentally here to stay. AI-driven applications are reshaping sectors from healthcare and finance to transportation and e-commerce. Unlike traditional software, AI systems learn from data and exhibit adaptive, often non-deterministic behavior. This complexity introduces new risks related to quality, reliability, fairness, and ethics. Effective testing of AI systems is essential for ensuring their safety, trustworthiness, and societal acceptance. Slide 5, Introduction. From vibe coding to vibe testing, the way we develop software is changing. Andrei Karpathy, a prominent figure in AI, tweeted that the hottest new programming language is English. This captures the essence of vibe coding, where developers use natural language to instruct large language models, LLMs, to generate code. It is a powerful new paradigm, offering unprecedented velocity and a significant leap from the traditional copy and paste of Stack Overflow snippets. However, this shift, while accelerating development, introduces new challenges for quality assurance. Vibe coding often abstracts the underlying logic, leading to a loss of intimate understanding of the code details and a greater reliance on the LLM's often non-deterministic output. If we are vibe coding, where the input is a high-level, sometimes ambiguous, natural language prompt, how do we ensure the quality and reliability of the code we produce? This leads us to the concept of vibe testing. Vibe testing shifts the focus of testing from meticulously checking every line of generated code to verifying the prompt to output contract. This involves a radical re-evaluation of the testing strategy. Instead of traditional unit testing being the primary gate, the emphasis moves to behavioral and integration testing to confirm the generated component satisfies the original, high-level natural language vibe or intent. This requires sophisticated, often AI-assisted, methods to automatically generate test cases that validate the code against the semantic understanding of the English prompt, rather than just against predefined, rigid inputs. The inherent non-determinism of LLM-generated code poses substantial challenges for the strict regulatory compliance required in medical devices, for example, making robust vibe testing a necessity, not just an efficiency gain. Slide 6, Introduction, From Vibe Coding to Vibe Testing, and this is not just a theoretical concept. Microsoft CEO, Satya Nadella, has stated that AI is already writing a massive portion of their code, confirming that 20 to 30% of the code in their repositories is now AI-generated. This number is rapidly trending upward, with some Microsoft leadership projecting that over 95% of all code will be AI-written by 2030. This makes the industry shift tangible and immediate, illustrating a profound transition away from hand-coded software. We are entering an era of vibe coders, where natural language is the new programming interface. Leaders from companies like Canva, Replit, and Google DeepMind are all embracing this shift, driven by the phenomenal increase in developer productivity, which is reported to be boosted by up to 50% in some cases. But as we celebrate this new age of accelerated development, we must also ask, what does this mean for quality assurance? How do we test code that is generated based on a vibe? This challenge is especially critical in domains requiring high assurance, like medical software. AI-generated code introduces two key quality problems: security vulnerabilities and comprehension debt. Studies have shown that a significant percentage of AI-generated code snippets contain security flaws, simply reproducing patterns from their training data. Furthermore, while code is created faster, developers often skip the critical step of reading and fully understanding it, leading to a phenomenon known as comprehension debt, which delays future modifications and debugging. The new testing paradigm, or vibe testing, must evolve to counteract these risks. The key lies in automated test generation and predictive analytics. Instead of writing tests for human-written code, we now use AI to generate tests from prompts. Tools are being developed to automatically create comprehensive test suites including unit, integration, and security tests directly from the original natural language vibe prompt, ensuring the output meets the semantic intent. 2. Employ metamorphic testing. A cutting-edge technique called metamorphic prompt testing involves rephrasing the initial prompt in a way that should not change the output's core function and then checking for consistency between the two generated code versions. Inconsistencies indicate a fundamental flaw, a hallucination, that traditional tests would miss. 3. Harness LLMs for mutation testing. New systems use LLMs to create highly realistic mutants, minor, deliberate faults, in the generated code and then use other LLMs to generate tests specifically designed to kill these mutants, thereby achieving a significantly higher standard of test coverage and compliance, which is crucial for medical software validation, for example. The future of quality is not less testing but testing that is exponentially smarter and more automated than the code it validates. Slide 7, Introduction, The Need for New Testing Paradigms, The Rapid Integration of AI into Our Digital and Physical Lives by 2025 signifies a profound shift. AI is no longer just a tool but an omnipresent, integrated layer, acting as the invisible operating system of the modern world. This deep integration is evident across industries, from AI-driven logistics optimizing global supply chains in real time to predictive maintenance systems in industrial IoT, which minimize downtime and save companies billions. AI is redefining productivity, creativity, and daily convenience, making human-AI collaboration an everyday reality. For instance, generative AI systems are now co-creating marketing campaigns and performing complex financial modeling, blurring the line between augmented and fully autonomous work. This widespread adoption necessitates a re-evaluation of our testing approaches, as traditional methods are proving insufficient for these complex, intelligent systems. The limitations of traditional testing stem from the non-deterministic and black box nature of large language models, LLMs, and deep learning systems. Unlike rule-based software, AI outputs are often probabilistic, meaning the same input can yield slightly different results, which is a significant challenge for predictable performance and load testing. Moreover, the primary concern shifts from verifying code correctness to validating model behavior and ethical alignment. This new reality demands a focus on specialized testing methodologies, such as adversarial testing to probe for vulnerabilities and bias, and explainable AI, XAI, testing to ensure the model's decision-making process is auditable and transparent, a critical requirement for medical software validation, for example, while dealing with regulatory compliance. AI is forcing quality assurance to evolve from merely checking functionality to rigorously validating trust, safety, and reliability at scale. Slide 8, Introduction, the need for new testing paradigms. While developers and software testers are enthusiastically embracing AI for tasks like vibe testing, essentially using AI to assist in testing, a critical question remains: who is responsible for validating, verifying, and testing the AI itself? There is a misconception that testing AI is just like testing traditional software. It sets the stage for discussing the fundamental differences and the need for specialized AI testing methodologies. The shift from traditional QA to AI auditing, the question of responsibility for AI validation and verification, V&V, is rapidly being addressed by the emergence of the dedicated AI auditor role. This is a crucial multidisciplinary function that moves beyond conventional quality assurance, QA. AI auditors, or specialized teams, are tasked with assessing the algorithm's safety, legality, and ethics across its entire lifecycle, from data collection to model deployment and continuous post-deployment monitoring. In regulated industries, like those requiring medical software validation, accountability rests heavily on the system designer and the quality management, QM, function, which often must provide independent verification and validation, 4&V, reports to regulatory bodies like the FDA. The key differences: predictable code versus probabilistic models. The primary reason traditional testing methods are insufficient is that the core object of testing is fundamentally different. 1. Determinism versus non-determinism. Traditional software is deterministic. The same input should always yield the exact same output. AI, particularly deep learning models, is non-deterministic and probabilistic. The output is a likelihood, not a certainty, making a simple expected result test case definition impossible and complicating standard performance and load testing techniques. 2. The black box problem. In traditional code, logic is explicit and debuggable. In AI, especially with large-scale LLMs, the decision-making path is often opaque, a black box. This demands a shift from testing functionality to testing behavior, fairness, and robustness. Specialized testing for explainable AI, XAI, is essential to make the model's rationale understandable for auditors and end users, especially for high-stakes applications like clinical diagnosis. 3. Data dependency and bias. AI's performance is intrinsically linked to its training data. Traditional software bugs are in the code. AI bugs, failures, biases, or unexpected behavior are frequently a result of flawed, incomplete, or biased data. This necessitates continuous bias and fairness testing to ensure the model does not discriminate against certain groups, a key ethical and legal requirement that standard regression tests cannot address. The comprehension debt refers to the gap between intellectually understanding a system or concept and truly internalizing it through experience. It is the time and effort it takes to understand code you did not write or a system you have not personally built, often leading to problems down the line. This is particularly relevant in software development when using AI-generated code, where developers might produce code quickly without fully grasping its logic, leading to difficulties in debugging and maintenance. Slide 9, Introduction, the need for new testing paradigms. We may think we have a lot of knowledge, both theoretical and practical, on what and how to test software applications. This includes decades of experience with established methodologies like functional, performance, security, and user acceptance testing, often built on the principle of deterministic outcomes. A vast body of knowledge has been established, both theoretical and practical, regarding how to test conventional software. However, the unique characteristics of AI systems challenge these established paradigms. The implicit question here is whether our existing expertise is truly adequate for the complexities introduced by AI, or if we need to develop entirely new frameworks and skills. The paradigm shift: deterministic versus probabilistic systems. The core difference lies in the nature of the systems themselves. Traditional software is inherently deterministic. A specific input is expected to always produce a predictable, verified output based on explicit code logic and business rules. Testing focuses on verifying that the code meets these fixed requirements, with clear pass or fail criteria, a test oracle. In contrast, AI systems are probabilistic. Their output is not determined by explicit programming but is generated from patterns learned during the training process on vast datasets. This introduces a critical challenge: the output is a statistical probability, not a guaranteed result. For example, a traditional system either calculates a loan interest rate correctly or incorrectly. An AI system, particularly in areas like medical diagnosis, may offer a diagnosis with an 85% confidence score. This shift moves the focus from verifying the code logic, functional testing, to validating the model behavior and training data, model quality assurance. New challenges beyond functionality. The complexity of AI systems introduces three primary challenges that traditional QA methods are ill-equipped to handle: data quality and bias. AI model performance is intrinsically tied to the quality, cleanliness, and representativeness of its training data. Testing must now start with data validation, checking for imbalances or biases in the dataset that could lead to unfair or discriminatory predictions in the real world, a non-functional requirement with significant ethical and regulatory weight. Lack of test oracle and explainability. Due to the black box nature of deep learning models, there is often a lack of a clear, single correct output, test oracle. Furthermore, the decision-making process is often opaque, making it difficult to trace why the AI delivered a specific result. New testing techniques must be applied to assess explainability and fairness in addition to traditional performance metrics. Model drift and continuous learning. Unlike a traditional application that remains static until the next release, AI models can degrade or drift over time as they encounter new, unanticipated data in production. This necessitates a continuous testing loop that includes real-time monitoring and robustness testing against adversarial data, a level of non-functional vigilance far exceeding conventional performance and load testing. Ultimately, the required skills are evolving from traditional automation and script writing to include competencies in data science, statistical analysis, ethics, and model performance metrics, such as precision, recall, and the score. Our existing expertise is the essential starting point, but it must be expanded to encompass these new, non-deterministic, and data-centric paradigms. Slide 10, Introduction. The need for new testing paradigms. Traditional software testing practices are insufficient for AI systems, which introduce unique complexities that demand a new approach to validation and quality assurance. Traditional methods, designed for deterministic and rule-based systems with reproducible results and clear cause-effect relationships, are inadequate for AI, as they rely on fixed scripts and predefined expected outcomes that assume consistent behavior across runs. In contrast, AI introduces probabilistic computations, where outputs vary due to stochastic, random, elements in models like neural networks, adaptive behavior that evolves with new data, data-dependent performance that hinges on training quality, and opaque decision-making processes that obscure internal logic. For instance, while traditional testing excels at repetitive tasks like regression checks, it struggles with AI's non-determinism, where the same input might yield different results, necessitating statistical validation instead of binary pass or fail criteria. This fundamental difference means that traditional QA approaches must evolve into AI-driven QA to effectively address the inherent uncertainty and complexity of AI systems, incorporating self-healing tests that automatically adapt to changes and predictive analytics to foresee potential failures before they occur. Recent advancements show that AI-powered tools can boost test accuracy by minimizing human errors and handling dynamic environments, such as generating test cases from natural language descriptions, which traditional methods cannot match. Moreover, in high-stakes domains, like autonomous driving, this shift is critical, as the traditional testing focus on reproducibility fails to capture AI's real-world variability, leading to gaps in safety assurance. By 2025, experts predict that over 80% of QA teams will integrate AI-driven methodologies to bridge these gaps, transforming testing from a reactive process to a proactive, intelligent ecosystem that enhances coverage and reduces maintenance overhead. Ultimately, this evolution not only addresses AI's challenges but also redefines QA as a strategic enabler for innovation, ensuring systems are robust, ethical, and reliable in an increasingly AI-centric world. Slide 11. The 4 core challenges in AI testing. Let us specify the core challenges that make AI testing distinct and complex, underscoring why conventional approaches are insufficient for ensuring the integrity of intelligent systems. We will explore 4 key dimensions: the black box nature of AI models, which obscures decision pathways and complicates debugging; their data dependency, where performance is only as good as the underlying datasets; their evolving behavior, marked by drifts that alter outputs over time; and the ethical considerations, encompassing bias and fairness that impact societal trust. Each of these presents unique hurdles that demand new perspectives and strategies, moving beyond conventional verification methodologies to ensure the reliability, fairness, and safety of AI systems. For example, the integration dilemma arises when selecting tools that must handle massive data volumes while avoiding technical debt from incompatible frameworks, a common pitfall in generative AI testing. Unpredictable results from small input variations further complicates the testing process, as AI's non-deterministic outputs defy standard reproducibility checks, requiring specialized statistical methods to validate consistency. In regulated sectors like healthcare, these challenges amplify, with data quality issues potentially leading to biased diagnostics that harm patients, as highlighted in recent OWASP, Open Worldwide Application Security Project, guidelines emphasizing privacy and ethical vulnerabilities unique to AI. Moreover, the storage and analytics burdens from sensor data in IoT integrated AI systems add layers of complexity, demanding scalable testing pipelines that traditional QA cannot support. Studies from 2025 indicate that up to 70% of AI projects face delays due to these unresolved challenges, underscoring the need for multidisciplinary teams skilled in ML-specific metrics like precision recall trade-offs. By addressing these dimensions holistically, organizations can mitigate risks, foster innovation, and build AI systems that not only perform but also align with human values and regulatory standards. Slide 12, Challenge 1, the black box. Many AI models, especially deep learning networks, are opaque, making it difficult to understand or debug their decisions. The first major challenge is the black box nature of many modern AI models, especially deep neural networks, where internal decision-making processes remain inscrutable to users, akin to peering into an opaque container where inputs enter and outputs emerge without visibility into the transformations within. Unlike traditional software where we can trace every line of code to pinpoint errors or biases, AI models often operate opaquely, making it incredibly difficult to understand how they arrive at a particular decision, identify the root causes of failures, or detect subtle biases embedded in learned patterns. This opacity not only hampers debugging but also raises accountability issues, particularly in critical applications like medical diagnostics, where unexplained decisions could lead to life-altering errors. Traditional white box testing, which relies on internal logic inspection, becomes ineffective here, as the black box shields the intricate web of weights and activations in deep learning layers from direct scrutiny. We need novel approaches to test these systems, even when their internal workings are not fully transparent, such as leveraging surrogate models or perturbation techniques to infer behaviors indirectly. A 2025 study on cybersecurity AI revealed that black box models missed 40% more vulnerabilities due to untraceable reasoning paths, prompting calls for mandatory explainability audits in high-risk deployments. Furthermore, this problem extends to ethical realms, where opaque decisions can perpetuate hidden prejudices from training data, eroding public trust in AI, evident in cases like facial recognition systems that underperform on diverse demographics. To counter this, emerging frameworks advocate for hybrid testing that combines black box probing with partial white box access where feasible, ensuring robustness without compromising model complexity. In essence, conquering the black box challenge is pivotal for transitioning AI from experimental tools to dependable production systems. Slide 13, Challenge 2, Data Dependency Challenges. AI systems depend heavily on the quality and representativeness of data. Issues like noise, missing values, or bias can degrade performance and fairness. The second challenge is data dependency, where the performance of any AI model is inextricably linked to the quality of its training data, turning data into the lifeblood and potential Achilles heel of intelligent systems. The common data quality issues are, as follows: bias, where historical prejudices in datasets lead to discriminatory outcomes, such as loan approval algorithms favoring certain demographics; noise, irrelevant or erroneous entries that degrade model accuracy by confusing learned patterns; mislabeling, incorrectly categorized data that instills systematic errors, like misidentified medical images skewing diagnostic tools; and data drift, gradual shifts in input distributions over time that cause models to falter in production environments. Poor data quality can propagate errors, impact predictability, and even lead to catastrophic model failure, as seen in a 2024 incident where an AI hiring tool amplified gender biases from outdated resumes, resulting in regulatory fines. Making rigorous data validation and comprehensive testing of data pipelines crucial, including techniques like synthetic data generation to augment scarce high-quality sources and anomaly detection to flag drifts in real time. In big data scenarios, handling diverse types, from structured tables to unstructured text, poses additional hurdles, with incomplete or non-compliant data impairing AI's ability to generalize, leading to flawed insights in sectors like finance. Best practices now emphasize pre-processing pipelines with automated checks for balance and representativeness, reducing error amplification that traditional software testing overlooks. A 2025 report notes that 60% of AI failures stem from data issues, underscoring the need for QA teams to adopt data-centric testing as a core competency to safeguard against these pervasive risks. Slide 14, Challenge 3, Evolving Behavior and Non-Reproducibility. AI models adapt over time, making consistent reproducibility of test results challenging. Testing must ensure equitable outcomes across demographic groups. The third challenge is the evolving behavior and non-reproducibility of AI systems, where models do not stay static but adapt and drift, defying the predictability that underpins traditional software validation. Unlike deterministic software, AI models can change their behavior over time due to factors like data drift, where input distributions evolve, for example, shifting user preferences and recommendation engines; concept drift, the evolution of underlying targets the AI learns, such as changing fraud patterns in banking; and stochastic training, non-deterministic algorithms yielding varied outcomes even with identical seeds due to random initializations. This means one-off testing is insufficient. Continuous monitoring, statistical validation, and longitudinal performance tracking are essential to ensure consistent and reliable performance, including reproducibility checks that recreate experiments under controlled environments to verify claims. In biomedical AI, for instance, evolving data complexities have led to 50% of studies failing reproducibility tests, highlighting flaws like data leakage or insufficient controls that later studies expose. To mitigate, practitioners employ versioning tools for datasets and models, alongside metrics like variance analysis to quantify instability, addressing the myth that ML's randomness inherently precludes reliable evaluation. A 2025 analysis reveals that 70% of AI research suffers irreproducibility due to immature practices, urging standardized documentation and computational access to boost trust and productivity. By embedding these safeguards, we transform potential pitfalls into opportunities for resilient, adaptive AI deployment. Slide 15. Challenge 4. Ethical considerations in AI testing. Testing must address privacy, security, and accountability to prevent harm and ensure transparency. AI can perpetuate or amplify societal biases present in training data. Testing must ensure equitable outcomes across demographic groups. The fourth critical challenge involves ethical considerations in AI testing, where ensuring systems do no harm requires proactive scrutiny of fairness, transparency, and accountability to prevent discriminatory outcomes and build societal trust. AI systems raise significant ethical concerns that must be addressed during testing, including algorithmic bias that perpetuates inequalities, privacy breaches from sensitive data handling, and opaque decisions that evade responsibility. This includes ensuring fairness by testing for bias in training data using algorithmic fairness metrics and mitigation tools, promoting transparency by tackling the black box issue with explainable AI, XAI, techniques like feature attribution, and guaranteeing safety and security through validation in real-world scenarios and adversarial robustness checks against manipulations. Demographic disparity reports and human, understandable rationales are key outputs, vital for compliance with regulations like the EU AI Act, which mandates ethical audits. And psychological applications, for example, AI tools must avoid harmful outputs by verifying accuracy and bias, while upholding confidentiality, a balance struck through human oversight. UNESCO's ethics framework emphasizes proportionality, data protection, and multi-stakeholder governance to align AI with human rights. A 2024 study in pathology AI highlighted privacy risks in training data, advocating for federated learning to anonymize contributions. Challenges like fairness in access and accuracy in assessments further complicate deployment, demanding holistic testing that integrates ethics from design to monitoring. By prioritizing these, we foster AI that is not only effective but equitable, mitigating societal harms and enhancing long-term adoption. Slide 16, AI Testing Dimensions Framework, New Theory of Software Testing. To tackle these complex challenges, we need a structured approach. The AI Testing Dimensions Framework is a model that outlines 5 key areas for quality assurance in AI systems. 1. Data integrity and quality, ensuring foundational reliability. 2. Non-deterministic behavior, managing probabilistic outputs. 3. Bias and fairness, upholding ethical equity. 4. Explainability, XAI, demystifying decisions. And 5. Robustness and security, fortifying against threats. Each dimension represents a critical aspect that requires specific methodologies and strategies to ensure the overall quality and trustworthiness of AI-based software, aligning with broader evaluation spectra that include human intelligence and ethics. AI testing encompasses methodologies for evaluating the functionality, performance, reliability, and ethical compliance of software systems that incorporate AI. Unlike traditional software, AI models require validation of learned behavior, data dependencies, and generalization to unseen data. AI testing spans the entire lifecycle, from data acquisition and model training to deployment and monitoring. Slide 17, Dimension 1, Data Integrity and Quality. AI systems depend heavily on the quality and representativeness of data. Issues like noise, missing values, or bias can degrade performance and fairness. Let us dive deeper into the first dimension of this, data integrity and quality, where we have established that an AI system's performance is fundamentally tied to its data input, making this the bedrock of effective testing. The common data quality issues are as follows: 1. Bias, 2. Noise, 3. Mislabeling, and 4. Data drift, and emphasizes why data quality is so critical, as flawed inputs can cascade into unreliable predictions, with studies showing that poor data accounts for 80% of AI project failures. Data is not just input, it is an intrinsic part of the system's logic, where imbalances lead to unfair outcomes, like biased credit scoring, and noise erodes precision in tasks like image recognition. Poor data can propagate errors and directly impact bias, unpredictability, and model failure, as evidenced by a 2025 case where outdated datasets caused a healthcare AI to misdiagnose 25% of cases. Therefore, rigorous data validation and comprehensive testing of data pipelines are not optional, they are essential, involving automated auditing tools to detect anomalies and synthetic augmentation for diversity. Best practices include federated learning to preserve privacy while enhancing quality, addressing environmental harms from data-intensive training. In software development, over-reliance on low-quality data risks complacency, amplifying errors in automated processes. By prioritizing this dimension, we build reliable AI systems that withstand real-world scrutiny and deliver equitable results. Slide 18, Dimension 2, Non-Deterministic Behavior. AI models adapt over time, making consistent reproducibility of test results challenging. Now for the second dimension, non-deterministic behavior, where AI models, especially those based on machine learning, can produce different outputs for the same input due to their probabilistic nature and continuous updates, introducing variability that challenges traditional testing quest for consistency. The goal of non-deterministic testing is to ensure consistent and reliable performance despite this inherent randomness, using advanced statistical tools rather than rigid assertions. The key testing approaches are, as follows: statistical validation, employing probability distribution analysis and confidence interval testing to quantify output reliability. Repeatability testing, running multiple executions with fixed seeds to measure stability across runs. Output variance analysis, tracking prediction variance to pinpoint unstable inputs like edge cases in generative models, and scenario-based evaluation, simulating representative and adversarial scenarios to probe robustness. In Power Apps, for instance, non-deterministic AI requires specialized validation to handle varying responses, preventing deployment surprises. Frameworks like metamorphic testing reorder inputs without altering semantics to detect inconsistencies, while traditional QA deterministic assumptions fail here, as small perturbations yield divergent results. A 2024 analysis showed that 91% of banks using AI for fraud detection grapple with this, necessitating eval frameworks for consistent scoring. LLM's probabilistic sampling further complicates this, demanding hybrid human-AI oversight for mission-critical apps. By mastering these techniques, we tame AI's unpredictability, ensuring deployments that are as dependable as they are innovative. Slide 19, Dimension 3, Bias and Fairness. AI can perpetuate or amplify societal biases present in training data. Testing must ensure equitable outcomes across demographic groups. The third dimension, bias and fairness, is a critical ethical and practical concern, as AI models can inadvertently learn and amplify biases present in their training data, leading to discriminatory outcomes that undermine trust and compliance. The importance of bias detection and mitigation is cited a 2024 study that showed bias detection in medical AI improved diagnostic accuracy for minority groups by 15%, by rebalancing datasets and applying fairness constraints. Well-discussed techniques like algorithmic fairness testing, using metrics such as disparate impact to flag inequalities, pre-processing methods, including reweighting samples or disparate impact removers to neutralize biases pre-training, demographic disparity reports, generating audits on performance across subgroups, and post-processing adjustments, like calibration or thresholding to equalize outcomes without sacrificing utility. In EHR-based models, systematic reviews from 2024 emphasize standardized reporting to unmask biases, revealing how incomplete disclosures hide discriminatory patterns. A UCL study amplified that AI not only inherits but exacerbates human biases, creating feedback loops in hiring and lending. Policy best practices advocate multi-stakeholder involvement for fair AI, integrating debiasing into SDLC. In auditing, downstream effects of biased AI demand rigorous testing to prevent financial inequities. These methods ensure fair outcomes while maintaining model performance, vital for equitable AI in diverse societies. Slide 20, Dimension 4, Explainability. XAI. Many AI models, especially deep learning networks, are opaque, making it difficult to understand or debug their decisions. The fourth dimension is explainability, XAI, which directly addresses the black box problem by rendering complex AI decisions interpretable, fostering trust and enabling informed oversight in opaque systems. Many complex AI systems, especially deep neural networks, make it challenging to interpret or justify their decisions, but XAI techniques bridge this gap for debugging, ethics, and robustness. There are key explainability techniques like SHAP, Shapley additive explanations, a gamed theoretic approach that fairly distributes feature contributions to predictions, offering global and local insights ideal for credit risk models where understanding influential factors aids compliance. And LIME, local interpretable model agnostic explanations, which perturbs inputs to build interpretable surrogates around predictions, versatile for any black box model, such as explaining image classifications in medical scans by highlighting salient pixels. SHAP excels in consistency across explanations, while LIME prioritizes local fidelity for quick insights, though both combat the opacity that erodes user confidence. In a 2024 tutorial, these were applied to neural networks, revealing how features drive outputs in ways humans can audit. Counterfactuals complement by showing minimal changes for alternative outcomes, enhancing what-if analysis and high-stakes decisions. Explainability is crucial for validating ethical considerations, improving model robustness against adversarial tweaks, and ultimately, building user trust, as non-interpretable AI risks regulatory backlash and adoption barriers. Slide 21, Dimension 5, Robustness and Security. Testing must address privacy, security, and accountability to prevent harm and ensure transparency. Our final dimension is robustness and security, where AI systems must withstand diverse threats to maintain integrity, from subtle manipulations to environmental shifts, ensuring they perform reliably in adversarial real-world contexts. The key areas of concern are, as follows: adversarial inputs, crafted perturbations that fool models like adding noise to evade fraud detectors, data drift, evolving distributions that degrade accuracy over time, unexpected variations, real-world deviations from training assumptions, and concept drift, task evolutions that render learned patterns obsolete. To address these, core testing strategies include adversarial robustness testing with tools like the Adversarial Robustness Toolbox to simulate attacks, continuous performance monitoring via dashboards tracking metrics in production, and drift detection algorithms that alert on statistical shifts, enabling timely retraining. The EU AI Act mandates accuracy and cybersecurity for high-risk systems, requiring lifecycle consistency. OWASP's guide highlights predictive AI vulnerabilities, recommending frameworks like ART for evasion testing. In 2025, AI validation platforms automate vulnerability scans, suggesting guardrails against poisoning and leaks. Robustness metrics augment standard evaluations, while ethical security prevents tampering, as per principles demanding tamper-proof designs. These ensure AI remains secure throughout its lifecycle, mitigating harms in dynamic deployments. Slide 22. Practical testing methodologies, new approach to software testing. Now that we have a framework for understanding the challenges and the dimensions, let us look at some practical testing methodologies that translate theory into actionable steps for hands-on AI software QA and testing. The key approaches are, as follows: 1. Model-based testing, generating cases from model specifications to verify behaviors. 2. Data-driven testing, leveraging datasets for comprehensive coverage including edge variants. 3. Adversarial testing, simulating attacks to harden resilience. And 4. AI-powered testing tools, automating generation and maintenance for efficiency. The next part of this presentation will elaborate on each of those practices. Slide 23. Practice 1. Model-based testing, MBT. Model-based testing, MBT, is a software testing methodology that uses abstract models such as state diagrams, workflows, or scenario-based representations to define the expected behavior of a system under test, SUT. These models serve as the foundation for automatically generating, executing, and maintaining test cases rather than relying on manually written scripts. In the context of AI software testing and QA, MBT is particularly adapted to handle the unique challenges of AI systems like machine learning, ML, models, where behavior can be non-deterministic, data-dependent, and prone to issues like bias or drift. Here, MBT often manifests as model test cases, which involve creating predefined scenarios, for example, edge cases in varying environmental conditions, to evaluate AI model performance against quantifiable expectations, such as achieving a specific mean average precision, MAP, in low-light scenarios. How to practically do it? Implementing MBT for AI software involves a structured, iterative process that leverages modeling tools and automation. A practical 5-step framework for AI ML systems, adapted from data-centric testing practices, is as follows. 1. Identify failure mode scenarios. Analyze the AI system's potential weak points, such as edge cases, outliers, or real-world variations. For example, for an autonomous parking AI, snow-covered lines, foggy weather, unusual camera angles, or new vehicle types. Use domain knowledge, historical data, or exploratory testing to brainstorm these. This step should be ongoing, revisiting during development and post-deployment. 2. Define model test cases. Translate scenarios into testable hypotheses with measurable outcomes. For example, the AI model must achieve 98% accuracy in detecting parking spaces when lines are 50% obscured by snow. Specify inputs, for example, data slices like snowy images, and expected behaviors, for example, metrics like precision, recall, or map. Tools like graphical modeling canvases, for example, BPMN importers and platforms like OpenText Value Edge, can help visualize these as workflows or state machines. 3. Evaluate granular performance. Run tests on targeted data slices using quality metrics to slice and analyze performance, for example, by brightness, blur, or object size. Automate this with open-source toolkits like Encode Active, which generates visualizations, for example, performance versus weather conditions, and computes metrics on predictions. Compare actual outputs against model expectations to flag failures. 4. Mitigate failure modes. If tests fail, apply targeted fixes, collect or augment data, for example, synthetic snow overlays on images. Relabel datasets with domain experts. Retrain the model on weak slices or use techniques like domain adaptation. Use similarity search on unlabeled data to prioritize relevant samples. 5. Automate and monitor. Integrate into CI/CD pipelines for continuous execution. Set up triggers, for example, rerun tests on new data batches, and dashboards for real-time monitoring of concept drift. Platforms like Ask UI or Eggplant DAI can blend MBT with agentic AI for dynamic exploration, regenerating tests by updating the model without rewriting scripts. Why is it important for QA of AI software? AI software introduces complexities like non-determinism, for example, varying outputs from the same input due to randomization, data sensitivity, ethical risks, for example, bias in facial recognition, and rapid evolution, for example, model updates causing regressions. Traditional QA struggles here because AI failures often emerge in untested edge cases or production environments, not lab conditions. MBT addresses this by providing systematic, broad coverage of scenarios, ensuring tests span diverse inputs like environmental variations or adversarial attacks while enabling faster iteration through automated generation. It promotes collaboration between QA, business analysts, and data scientists via shared models. Reduces maintenance overhead, update one model, regenerate all tests, and shifts QA to proactive risk mitigation. In AI contexts, pairing MBT with agentic AI adds adaptability, like auto-exploring UI changes in AI-driven apps, leading to fewer bugs, higher reliability, and compliance with standards like ISO/IEC 25010 for trustworthy AI. Ultimately, it builds confidence in AI deployments by quantifying performance in real-world what-if situations, minimizing costly post-release fixes. What part of traditional software testing would it upgrade and update? MBT primarily upgrades test case design, generation, and maintenance in traditional software testing, which often relies on manual scripting or aggregate metrics, for example, overall accuracy scores. Traditional methods excel in deterministic systems but falter in AI's dynamic nature. Scripts break with UI. The model changes, and broad metrics hide granular failures. For example, a model with 95% average accuracy failing 50% in rain. MBT updates this by automating generation, derives exhaustive test suites from models, covering more paths than handcrafted cases, reducing design time by 50 to 70%. Enhancing maintenance, model tweaks propagate to all tests, unlike script-by-script updates, cutting effort in evolving AI systems. Enabling granularity and adaptability, shifts from static, code-heavy tests to scenario-driven, data-sliced evaluation, integrating AI tools for self-healing, for example, agentic recovery from drifts. Boosting collaboration and coverage, involves non-coders via graphical models and smart algorithms, improving alignment with requirements over siloed scripting. This evolution makes testing more efficient, scalable, and AI-native, bridging the gap between traditional unit integration tests and AI's need for continuous, scenario-based validation. Slide 24. Practice 1. Model-based testing, MBT, example, ECG, model-based testing, MBT, is highly relevant for testing electrocardiogram, ECG, medical systems, which are safety-critical cyber-physical devices that process electrical heart signals to detect arrhythmias, monitor vital signs, and support diagnostics. These systems integrate hardware, for example, electrodes, amplifiers, ADCs, embedded software, for example, special microcontrollers, and often AI/ML components for pattern recognition, making them prone to faults in signal conditioning, timing, or decision logic that could lead to misdiagnosis or device recalls. Traditional open-loop testing, for example, replaying pre-recorded signals, misses closed-loop interactions, such as how device outputs affect heart rhythm in implantable systems like pacemakers tied to ECG sensing. MBT addresses this by using executable models of physiological behaviors, for example, heart conduction via timed automata, to generate realistic, diverse test scenarios, including edge cases like premature ventricular contractions, PVCs, inducing tachycardia. For AI-enhanced ECG systems, MBT ensures the model's robustness against noisy or adversarial inputs by simulating physiological variations, aligning with regulatory needs like FDA's emphasis on verifiable safety in Class 3 devices. Studies show MBT uncovers issues like pacemaker-mediated tachycardia, PMT, that open-loop methods overlook, directly improving reliability in cardiac monitoring. Slide 25. Practice 1. Model-based testing, MBT, example, ECG, continued. MBT is practically feasible for ECG systems, particularly in development and verification phases, though it requires domain expertise and tools. Implementation often follows a cyber-physical modeling workflow, as demonstrated in pacemaker testing adaptable to ECG analyzers, model construction, develop a virtual heart model, VHM, using timed automata or UML activity diagrams to represent heart electrophysiology, for example, sinus rhythm, AV node delays of 230 to 300 milliseconds effective refractory period. For ECG, this generates synthetic signals mimicking PQRST waves, validated against clinical electrogram data. Device modeling, abstract the ECG system's behavior, for example, signal amplification from 0.5 to 4 mV, filtering 0.01 to 250 Hz, QT interval calculation via Bazit's formula, as state machines, integrating hardware interfaces like ADCs. Closed-loop composition and test generation, combine models, for example, in Simulink, Stateflow or UPL, to simulate interactions. Use algorithms like depth-first search on activity flow graphs to auto-generate test paths covering branches, for example, arrhythmia detection thresholds. Execution and validation, run simulations, then physical tests on FPGA or hardware-in-the-loop setups for multi-level testing. Adapt abstract tests via input-output adapters across software unit, integration, hardware-software, and system levels. Iteration and monitoring, refine models with real patient data, ensuring coverage of 100% paths and compliance via formal verification. Tools like Simulink enable real-time simulation and code generation, while adapters reduce test maintenance by 50 to 70% through reuse. In a diabetes IOHT case, extensible to ECG for heart rate monitoring, MBT generated 5 comprehensive test sequences from UML diagrams, detecting UI and logic faults efficiently. For implantable cardiac devices, FPGA-based VHM exposed ELT faults in DDD mode pacemakers, validating against EP studies. Benefits: automates exhaustive coverage for complex scenarios, cuts costs by early fault detection, for example, integration issues at hardware-software level, supports reusability in embedded systems, and aids regulatory documentation for closed-loop efficacy. Challenges and limitations: high initial modeling effort for accurate physiology, for example, nonlinear conduction, limited industry adoption due to complexity in large UML graphs. Assumes deterministic behaviors, potentially missing AI non-determinism, requires expertise in formal methods and validation against diverse patient data. Despite this, it is scalable for ECG via abstractions, with evidence from recalls, for example, 21% software related by 2006, underscoring its value over manual methods. Overall, MBT shifts ECG testing from reactive to proactive, making it a practical upgrade for AI-integrated systems in high-stakes healthcare. Slide 26, Practice 1, Model-Based Testing, MBT, continued. To summarize, model-based testing, MBT, uses abstract models to represent a system's desired behavior. These models automatically generate test cases, enhancing test coverage and reducing manual effort, particularly for complex AI systems. MBT involves creating models, for example, state machines, flowcharts, describing the system's behavior. Test cases are then automatically generated from these models, executed, and results are compared against expected outcomes. AI can enhance model creation and test generation. MBT is particularly useful when testing complex AI systems with numerous states and behaviors, where manual test case generation is impractical or error-prone. It is applied throughout the development lifecycle, from design to maintenance. MBT improves test efficiency, coverage, and quality by automating test generation and maintenance. For AI systems, it helps manage complexity, identify edge cases, and ensure reliable behavior in dynamic environments, reducing human error. In traditional software testing, MBT's ancestors include techniques like finite state machine testing, decision table testing, and cause-effect graphing. These methods also use formal models to derive test cases, focusing on system states and transitions. Slide 27, Practice 2, Data-Driven Testing, DDT. Data-Driven Testing, DDT, is a software testing methodology that separates test logic from test data, allowing a single reusable test script to execute multiple times against varied input datasets stored externally such as in CSV files, spreadsheets, databases, or JSON XML formats to validate different scenarios efficiently. In the context of AI software testing and QA, DDT is particularly valuable for handling the data-intensive and probabilistic nature of AI/ML systems, where models must be evaluated across diverse inputs like augmented images, synthetic physiological signals, or user behavior logs to detect issues such as bias, overfitting, or performance degradation in specific data slices. How to practically do it? Practically implementing DDT for AI software involves a structured approach that emphasizes automation, reusability, and integration with data pipelines. Here's a step-by-step guide adapted for AI/ML contexts, 1. Identify and design test scenarios, define functional requirements and edge cases relevant to the AI system. For example, for an ML-based fraud detection model, valid transactions, anomalous patterns, or imbalanced classes. Categorize into positive, negative tests and specify inputs, expected outputs, such as prediction accuracy thresholds. 2. Prepare external data sources, create or curate datasets in accessible formats. For AI, use tools like Pandas to generate CSV files with columns for inputs, for example, transaction features, labels, and metrics, for example, F1 score greater than 0.85. Incorporate synthetic data via libraries like SDV for privacy-preserving augmentation, or slice real datasets by attributes like demographics to test for bias. 3. Develop the reusable test script. Write a generic script that reads from the data source and iterates over rows. This runs the test per data row, logging failures with details. 4. Execute, analyze, and integrate. Run via CI/CD tools like Jenkins, using analytics for prioritization, for example, ML to predict high-risk data subsets. Generate reports with tools like Allure, visualizing pass rates by data slices, for example, low performance on minority classes. 5. Maintain and optimize, update data sources for new model versions or drift detection without altering scripts. Leverage AI for self-healing, for example, auto-adjusting locators in UI tests, and predictive selection to focus on likely failures. Start small with 10 to 20 datasets, scaling with frameworks like Selenium for UI or TensorFlow testing for models. Best practices include using realistic data, validating negative cases, and ensuring traceability in logs. Why is it important for QA of AI software? DDT is essential for AI software QA due to the inherent data dependency and variability of ML models, where single-run tests often miss subtle failures like reduced accuracy on underrepresented data or adversarial inputs, potentially leading to biased decisions in production, for example, erroneous diagnoses in healthcare AI. By enabling exhaustive evaluation across thousands of data variations, DDT uncovers these granular issues early, improving robustness and compliance with standards like the EU AI Act. AI enhancements to DDT, such as predictive test selection via ML models analyzing historical defects, shorten CI/CD cycles by 25 to 30%, reduce defect leakage, and optimize coverage for real user behaviors, as seen in e-commerce platforms simulating personalized journeys. In high-stakes AI domains like finance or healthcare, it supports synthetic data generation for privacy, for example, GDPR-compliant testing and anomaly detection, fostering faster, more reliable releases while cutting manual effort by up to 40%. What part of traditional software testing would it upgrade and update? DDT primarily upgrades test case generation, execution, and maintenance in traditional software testing, which relies on hard-coded inputs and manual repetition for multiple scenarios, leading to inefficiency, low coverage, often less than 30%, and high error rates in data-heavy AI contexts. Traditional methods like equivalence partitioning offer broad categorization but fail to scale for AI's vast input spaces, missing slice-specific failures, for example, bias in demographic subsets. DDT updates this by externalizing data for automated parameterization, enabling 2-5x broader coverage with reusable scripts that adapt via analytics-driven prioritization and self-healing AI. It shifts from reactive, static workflows to predictive, dynamic ones, replacing manual data embedding with optimized generation from user logs and historical patterns, reducing redundancy, execution time, and costs while enhancing maintainability, for example, data updates without code changes. This evolution integrates continuous feedback loops, making testing more scalable and AI-native compared to one-off, theory-based approaches. Slide 28, Practice 2, Data-Driven Testing, DDT. Data-Driven Testing, DDT, is a software testing approach where test data is stored externally. It allows the same test script to execute with various input datasets, validating different scenarios and improving test coverage for AI systems. DDT separates test logic from test data. Test scripts read input data from external sources, for example, spreadsheets, databases, and execute the same test case multiple times with different data. This is crucial for testing AI models with diverse datasets. DDT is essential for AI systems where model performance heavily depends on data quality and diversity. It is used when testing various inputs, edge cases, and scenarios to ensure robustness, fairness, and accuracy across different data distributions. DDT enhances test coverage and efficiency for AI systems by enabling comprehensive validation with diverse data. It reduces test script maintenance, identifies data-related issues, and ensures AI models generalize well to unseen data, improving reliability. In traditional software testing, DDT's ancestor is parameterization, where test cases are executed with different sets of input parameters. This concept evolved to externalize data, making tests more flexible and reusable across various scenarios. Slide 29, Practice 3, Adversarial Testing. Adversarial testing, in the context of AI software testing and QA, is a specialized security and robustness evaluation technique that involves deliberately crafting and inputting misleading, perturbed, or malicious data known as adversarial examples to an AI system to expose vulnerabilities, biases, or failure modes that standard tests might miss. These examples are designed to appear benign or nearly identical to legitimate inputs from a human perspective but cause the AI model to produce incorrect outputs, such as misclassifications in image recognition or harmful responses from a chatbot. It simulates real-world attacks or edge cases, like subtle image alterations fooling autonomous vehicle perception or prompt injections bypassing safety filters in generative AI, making it essential for assessing the integrity and trustworthiness of AI/ML models. How to practically do it? Practically implementing adversarial testing for AI software requires a systematic, iterative process that combines manual crafting, automation tools, and human oversight. Here is a step-by-step guide, drawing from established practices. 1. Define testing objectives and scope. Identify key risks, such as policy violations, for example, generating harmful content, biases and sensitive attributes, for example, race or age, or robustness to perturbations, for example, noise and audio for voice recognition. Target specific behaviors like semantic misunderstandings or state transitions in LLMs. 2. Gather or generate adversarial inputs. Create diverse tricky data sets. For white box testing, with model access, use optimization algorithms to perturb inputs minimally, for example, adding imperceptible noise to images. For black box, input-output only, rely on query-based attacks. Tools like the Adversarial Robustness Toolbox, ART, or CleverHans can automate this. For example, generate fast gradient sign method, FGSM, attacks on a neural network by slightly altering pixel values to flip classifications. 3. Execute tests and observe outputs. Feed inputs into the AI system, for example, via API or UI, and capture responses. Use automated scripts for scale, for example, in test rigor, write plain English tests like, enter hello, can you help me, in message AI chat, spelling errors, enter. Check that page contains a positive response from the chatbot using AI. Run thousands of iterations, logging predictions and metrics like attack success rate, ASR. 4. Analyze and document failures. Employ human annotators or AI explainers to evaluate outputs for issues like inaccuracies, biases, or exploits. Compute robustness metrics, for example, ASR less than 5% for strong models, and visualize failures, for example, confusion matrices for perturbed versus clean data. 5. Mitigate and iterate. Retrain the model with adversarial examples, add defenses like input sanitization, or implement runtime monitoring. Retest post-mitigation and integrate into CI/CD pipelines for continuous validation. Start with open-source libraries like Fullbox for quick prototypes, scaling to enterprise tools like TestRigger for low-code automation. For generative AI, focus on prompt-based attacks like instruction sandwiching, for example, embedding unsafe requests in benign queries. Why is it important for QA of AI software? Adversarial testing is crucial for AI software QA because AI systems are inherently brittle to subtle manipulations, where even minor input changes can lead to catastrophic failures such as misdiagnosing medical images or enabling fraud in financial AI, undermining reliability in high-stakes applications. It proactively uncovers exploitable weaknesses, biases amplified from training data, and non-deterministic behaviors before deployment, enhancing security against real threats like model poisoning or evasion attacks. In regulated environments, it ensures compliance with standards like the OWASP AI Testing Guide, promoting ethical AI by addressing privacy risks and building user trust through transparent vulnerability disclosure. Ultimately, it shifts QA from reactive bug fixing to resilient design, reducing post-release incidents by simulating adversarial conditions that traditional data can't replicate. What part of traditional software testing would it upgrade and update? Adversarial testing primarily upgrades security and edge case testing in traditional software testing, which typically focuses on functional validation with standard inputs and rule-based checks, often overlooking AI's probabilistic vulnerabilities to crafted perturbations or black box opacity. Traditional methods like boundary value analysis handle obvious edges but fail against AI-specific threats like adversarial examples, leading to incomplete coverage in non-deterministic systems. It updates this by introducing offensive, simulation-driven assessments that incorporate human-AI hybrid evaluation and data-centered defenses, for example, retraining on attacks, extending beyond static code reviews to ongoing monitoring for data drift. This evolution enables scalable, automated probing of failure modes, reducing manual effort while boosting robustness metrics, transforming siloed security tests into integrated, lifecycle-wide practices tailored for AI's unique risks. Slide 30. Practice 3. Adversarial testing. Adversarial testing involves systematically evaluating AI models with intentionally crafted malicious or deceptive inputs. The goal is to expose vulnerabilities, weaknesses, and unexpected behaviors that could lead to incorrect decisions or system failures. Testers generate adversarial examples by making subtle perturbations to legitimate inputs, aiming to trick the AI model. Techniques include fast gradient sign method, FGSM, or projected gradient descent, PGD, to create inputs that cause misclassification or undesired outputs. Adversarial testing is crucial for AI systems deployed in sensitive applications, for example, autonomous driving, cybersecurity, finance, where robustness and reliability are paramount. It is performed during development and post-deployment to continuously assess model resilience. It is vital to ensure AI systems are robust against malicious attacks and unexpected inputs. Adversarial testing helps uncover vulnerabilities, improve model security, and enhance trustworthiness, preventing potential exploitation, safety risks, or biased outcomes in real-world scenarios. In traditional software testing, the closest ancestor is penetration testing or fuzz testing. These methods also involve intentionally providing unexpected or malformed inputs to uncover security vulnerabilities or robustness issues in software systems. Slide 31. Practice 4. AI-powered testing tools. AI-powered testing tools for automating test case generation, execution, and adaptation to changes. AI-powered software testing tools are automated solutions that leverage machine learning, ML, natural language processing, NLP, and computer vision to enhance, automate, and streamline the entire testing process. These tools go beyond simple script execution to provide intelligence and resilience. Modern AI-powered software testing tools utilize several key features to enhance quality assurance. Self-healing automation is a critical capability that uses AI to detect and automatically adapt test scripts when UI elements, like a button ID, shift, which is vital as it significantly reduces maintenance overhead, a critical factor in preparing a stable suite for activities like load testing. Additionally, visual AI testing employs computer vision to test the application's appearance, layout, and overall user experience, UX, as a human would, Rather than relying on brittle pixel-by-pixel comparisons, this helps catch visual bugs and regression often missed by traditional functional tests. To accelerate and democratize test creation, many tools include natural language processing, NLP, integration, which enables all testers, including non-technical ones, to create test cases by simply describing the required steps in plain English, codeless testing, thereby accelerating test creation. Finally, predictive analytics analyzes historical data, such as defect logs and code changes, to predict high-risk areas of the application that require more focused testing, allowing teams to optimize test prioritization and improve overall test coverage efficiency. Automated test generation, AI significantly accelerates test creation by automating the generation of test cases, test data, and even full test scripts. Analysis-driven generation, ML algorithms analyze requirements documents, user stories, existing code structure, and historical user interaction data to automatically generate comprehensive and relevant test cases. This ensures broader test coverage, including edge cases. Generative AI for scenarios, large language models, LLMs, can translate high-level business logic or user flows, written in natural language, into executable test scripts and suggest diverse, realistic scenarios for functional, API, or performance and load testing. Synthetic data generation, AI can generate high volumes of synthetic yet realistic test data, which is especially important for areas involving medical software validation where real-world patient data is sensitive or scarce. Solving the oracle problem. The test oracle problem is the fundamental challenge in testing, determining whether a system's observed output for a given input is correct or incorrect when no explicit, easy-to-check specification exists, for example, in complex or non-deterministic systems. AI helps solve this by dynamic oracle generation. ML models analyze existing system behavior, specifications, and test results to learn and dynamically infer the expected output. This is a form of self-correction that automates the pass or fail determination. Predictive oracles. For performance-critical systems, AI can analyze past performance metrics, latency, throughput, to establish a baseline and predict the expected performance response under new load conditions. Any deviation from this predicted performance window is flagged as a failure, automating the validation step in load testing. Consistency checks. AI can compare the output of multiple redundant implementations or check for consistency across different runs or platforms, a technique known as metamorphic testing. The oracle is then defined as the expectation that related inputs should produce related outputs. Production monitoring. The role of AI extends beyond pre-release QA into continuous quality assurance by monitoring the application when it's live in production. This is often integrated with performance and load testing follow-up. Real-time anomaly detection. AI continuously analyzes massive streams of production data, logs, metrics, user interactions, to identify unusual patterns or subtle defects that were not caught in testing. Because AI understands the normal baseline, it can instantly flag deviations as potential issues. Predictive defect prevention. By correlating real-time performance data with code commits or deployment events, AI can not only detect a problem but also suggest the likely root cause or even predict a failure before it becomes catastrophic, allowing for proactive intervention. Self-healing in production. In some systems, AI can be used to trigger automated remediation actions, such as rolling back a bad deployment or reallocating resources, directly addressing system stability, a key concern for any performance and load testing expert. User behavior monitoring. Analyzing production usage data helps QA teams understand which parts of the application are most frequently used or problematic in the real world, leading to a smarter, risk-based prioritization of future testing efforts. Both Catalan Studio and Testim belong to the group of AI-powered software testing tools because they both integrate artificial intelligence and machine learning capabilities directly into the core of their test automation platforms to significantly improve test creation, execution, and maintenance. Slide 32. Practice 4, AI-powered testing tools 1. Catalan Studio. Catalan Studio utilizes AI to enhance several aspects of the testing lifecycle, making test automation more efficient and resilient. Catalan Studio is recognized as an AI-powered tool because it leverages AI and machine learning to make test automation more efficient and resilient across the entire testing lifecycle. A core feature is self-healing and smart test maintenance, where the AI engine actively detects changes in the application's UI elements, locators, and automatically suggests or applies modifications to keep test scripts valid, thereby vastly reducing maintenance time. Furthermore, it accelerates the test authoring process through AI-powered test case creation, features like True Test capture real user interactions to automatically generate new test cases and test data, effectively modeling user behavior to ensure comprehensive test coverage. The platform also incorporates generative AI via the Studio Assist feature, which can generate test code from plain language descriptions and explain existing code, often powered by GPT technology. For comprehensive quality checks, Catalan uses visual testing. AI algorithms compare screenshots across different builds to automatically flag visual discrepancies that genuinely affect the human user experience, moving beyond brittle pixel-by-pixel checks. Lastly, the platform's smart waits capability ensures test reliability by intelligently pausing test execution until all necessary elements are fully loaded, which significantly reduces false test failures or flakiness. Slide 33, Practice 4, AI-powered testing tools 2. TestHim. TestHim is built with AI at its core, primarily focusing on stability and faster test authoring, particularly for dynamic web and mobile applications. TestHim's position as a leading AI-powered test automation tool is secured by its focus on stability and efficiency, which directly aids in maintaining the resilience of large test suites necessary for continuous delivery. Its signature feature is AI-powered smart locators. This functionality uses sophisticated machine learning models to evaluate hundreds of attributes for a UI element, going far beyond brittle single locators like XPath or CSS. If one attribute changes, the AI uses the others to reliably locate the element and self-heal the test, thus ensuring exceptional stability. Building on this, self-healing and auto-improvement means the AI learns from past runs. When elements shift, the AI-powered locators adjust to the change, and the system can automatically suggest fixes upon test failure, thereby drastically minimizing test maintenance efforts. To boost productivity, TestHim includes generative AI, TestHim Copilot, which allows users to quickly generate custom code steps using natural language input, facilitates debugging of existing code, and helps developers gain a swift understanding of test code. Finally, the feature of automatic grouping leverages AI to observe repeated sequences of steps across multiple tests, automatically suggesting and creating reusable components. This directly streamlines test architecture and significantly reduces the effort required for long-term test maintenance. Slide 34. Practice 4, AI-powered testing tools. Continued, AI-powered testing tools leverage AI and machine learning to enhance various aspects of software testing. They automate test case generation, optimize test suites, predict defects, and analyze test results, improving efficiency and coverage for AI systems. These tools use AI algorithms for tasks like natural language processing to understand requirements, computer vision for UI testing, and predictive analytics for risk assessment. They can generate test data, self-heal broken tests, and provide intelligent insights into test failures. AI-powered tools are beneficial throughout the entire software development lifecycle, especially for complex AI systems. They are used for continuous testing, regression testing, performance testing, and exploratory testing to handle dynamic environments and large datasets. They significantly reduce manual effort, accelerate testing cycles, and improve the accuracy of defect detection. For AI systems, these tools are crucial for managing complexity, ensuring quality, and adapting to rapidly evolving models and data, leading to faster releases. The ancestors include traditional test automation frameworks, for example, Selenium, Appium, and test management tools. AI-powered tools build upon these by adding intelligent capabilities like self-healing tests, predictive analytics, and smart test case generation. Slide 35, Real-World Applications. 1. Autonomous Vehicles. Let us examine a real-world example, autonomous driving, a high-stakes AI arena where testing is paramount for safety. This example presents how our dimensions apply: data integrity for sensor datasets, non-deterministic behavior in perception systems, bias and fairness for equitable road responses, explainability for accident forensics, robustness against hacks. In Waymo's case, ML fused LiDAR and cameras for 99% object detection, but drifts required continuous SIMs. Tesla's autopilot uses neural nets for lane changes, safer than humans per stats. Gen AI optimizes designs, while EU regs demand robustness testing. Kia's predictive maintenance cuts costs 20%. These ensure safe, reliable AVs. Slide 36, Real-World Applications. 2. Medical Diagnosis. Medical Diagnosis AI, where errors bear severe consequences, demanding meticulous testing. Dimensions apply: XAI for rationale trust, fairness to equalize care, with bias detection boosting minority accuracy 15%. GPT-4 diagnosed 57% of complex cases, outperforming humans. In pneumonia risk, neural nets guide admissions accurately. Cardiology AI reshaped outcomes via real-time analysis. UVA studies show AI aids but needs explanations to enhance diagnoses. Eye disease detectors exemplify precision gains. These validate AI's diagnostic revolution. Slide 37, Real-World Applications. 3. Financial Fraud Detection. Financial institutions leverage AI for real-time fraud detection, employing sophisticated testing for protection. Adversarial testing simulates attacks, data-driven probes anomalies, ethical checks ensure fairness. Results: 91% U.S. banks use AI, cutting false positives 30%. NVIDIA's holistic views boost accuracy, Elastic's Gen AI scores transactions instantly. Conduit Scalability detects evolving threats, Mind Bridge monitors all TXNS. Infosys flags anomalies real-time, FeedSeye's platform secures channels. These yield impressive reductions in fraud losses. Slide 38, Conclusion. A paradigm shift in QA. Testing AI systems necessitates a fundamental paradigm shift from traditional software quality assurance approaches, as AI's probabilistic and opaque nature renders script-based methods obsolete. The unique characteristics demand a multi-dimensional and systematic approach throughout the lifecycle, including rigorous data validation, comprehensive fairness checks, robust adversarial testing, and continuous monitoring to preempt drifts and biases. This path forward bridges theory with practice, leveraging Gen AI for proactive QA that predicts defects from logs. In 2025, AI reshapes QE, shifting from reactive to intelligent assurance via self-healing tools. Agentic AI accelerates this, enabling scriptless scalability. Embracing this ensures reliable, ethical intelligent systems. Slide 39, Conclusion. A paradigm shift in QA. AI rise demands moving beyond traditional testing to AI-tailored principles, addressing technical, ethical, and social imperatives. This shift, powered by LLMs, views AI as integral, demanding new QA paradigms for production paths. By systematizing multi-dimensional testing, we deploy safe, fair AI beneficial to all, revolutionizing quality assurance. Slide 40, Contact Information. Thank you for your attention. I am now happy to answer any questions you may have. Here is my contact information as a QR code for scanning. Please feel free to reach out to me if you have any further questions or would like to discuss this topic in more detail. This presentation was brought to you by ginsbourg.co.il.